My name is Francisco Eduardo Balart-Sanchez, and today I'm going to talk about my article titled On Mass Spring System Implementation in Cluster-Based Manets for Natural Disaster Applications. Currently, I'm pursuing the PhD at the Western Institute of Technology and Higher Education, and also I'm working at Amazon as a quality assurance engineer. Today, we'll talk about what manets are, the role of a backbone in a manet, the cluster-based algorithm that we use to construct a manet backbone, and the implementation of a mass spring model on such algorithm. Survivors have more probability of survival when found within the initial 72 hours. This is known as the golden rule. Due to the catastrophe, common communication systems such as cellular communication, local Wi-Fi access point, and other wired networks are usually down. Therefore, Manet's advantage over wired networks show promise on search and rescue operations. So, what are Manets? Manet stands for Mobile Ad-hoc Network, and you can think in a Manet as a circularless, non-centralized network. This network can be composed by laptops, drones, and smartphones, among others, which communicate among themselves by wireless links. There are already applications based on Manets such as FireChat and BridgeFi. So, Manet main characteristics are they are usually energy constrained, mobile, self-organized, and the topology is dynamic. Due to the aforementioned, we need a way to have an efficient communication and good topology management. That's where backbones on Manets came to play. For the backbone construction and maintenance, we have chosen the energy-efficient self-organized algorithm, also called EESOA. This scheme is a cluster-based algorithm. So how does it work? EESOA algorithm works as follows. All the nodes will gather information of their neighbors within one hub. Then it will self-assign a role. This is a four-hierarchy cluster-based algorithm. The node with more neighbors and residual energy will be called leader, and then it would start inhibit the neighbors. A node inhibited by a single leader is called a member. A node inhibited by more than one leader will be called a gateway. And a member that is connecting to another member from another cluster will be called a bridge. Even though EESOA solved the backbone communication problem, we need to ensure the connectivity of the network. In this article, we have chosen the implementation of the mass spring model with an equilibrium distance L, as shown on equation 1. L distance will be defined within the communication range of the nodes. Therefore, all EESOA nodes will generate a mass spring model against all the neighbors, maintaining an equilibrium distance L, and therefore maintaining a connected network. In this example, I show you two snapshots of a dense Manet deployment with a spread and dense survival deployment. In our research, we simulated four scenarios: dense Manet deployment with dense survival deployment, dense Manet deployment with spread survival deployment, spread Manet deployment with spread survival deployment, and spread Manet deployment with dense survival deployment. In this simulation, you will see red blobs, in which this case mean the Manet backbone. Also, you can see how the Manet nodes reach the survivors, forming a wireless link. Let's see the results now. Here I can show you an example of the simulation, which was a Java-based simulator using the GraphStream library. Simulation starts and EESOA nodes start to converging by generating the mass spring models and generating repulsive and attractive force, when the attractive force will have as limit the equilibrium distance L. The red blobs are the main backbone communication, and you can see how the nodes self-assign the node. In this case, we found 29 survivors of the 30, and we have a final distance of 1,370 meters from the ideal one, which is 1,500. we chose 15 nodes on a 50 by 50 meters area and 30 survivors. For performance parameters, we chose coverage area and total number of survivors found. In terms of coverage area, we can see that regardless of the survivor deployment, a dense Manet deployment shows better performance in terms of coverage area. In this case being the ideal area of 1,500 meters, we can observe that a dense Manet deployment shows better performance in the ten simulations performed. In terms of survivors found, although the results were not as clear as in coverage area, we can see a better performance when the deployment of the Manet was dense, regardless of the deployment of the survivors was dense or spread. This is thanks to the mass spring implementation on the EESOA nodes, which causes the network to expand while maintaining a communication range, which is defined by the equilibrium distance L. So, what we can conclude about this work? The mass spring implementation on the EESOA showed better performance when the Manet deployment was dense, regardless if the deployment of the survivors was dense or spread. There is a main trade-off when using a mass spring implementation. We ensure a connectivity on the network, but due to the equilibrium distance L, nodes will have an overlapping area, therefore limiting the coverage area for rescue operations. For future work, we need to take into account that the main connections that we care about are with the survivors and with the backbone and cluster head. Thanks. I hope you enjoyed this presentation, and please don't hesitate on sending me an email which you can find in the second slide of this presentation.